G'day grade 12s, we're looking at question 7 of the EC September 2019 paper. Acid-base indicators are generally represented by the formula given there. The reaction with water can be represented by the following equations. So the indicator that reacts with the H2O gives us the hydronium ion, with the indicator that gives us a colorless first, and then we get pink after. This says acid-base indicators are considered to be weak acids. Define the term weak acid. So this is a term which I'm going to say verbally. It's a weak acids. What they do, they ionize completely in water. So I'm just going to write down the key phrase here, that it ionizes completely in water. Okay, it ionizes completely in water and to form a lower concentration of hydronium ions. Okay, so let's put it this way: low concentration of hydronium, which is H3O plus ions that are formed. So weak acids, they ionize completely in water to form low concentrations of H3O plus ions. And then 7.1.2 is our next question. Is H2O, water, is it acting as an acid or is it acting as a base in this reaction? Well, if we look here, we can definitely see that we are missing a hydrogen here. So you can see that's the same there as it is here. So it looks like water is definitely acting as a base in this reaction. Right? That's just by looking at where the hydrogen has disappeared from. Right? We know acid is a proton donor and a base is a proton acceptor. They ask us here to write down the formula of the conjugate base of this indicator over here. Well, we know that a conjugate base forms as a result of an acid donating a proton. If an acid donates a proton, we can clearly see the acid donated a proton to the base, which was water, leaving what is left after the acid has donated a proton. What is left is called the conjugate base. This is clearly our conjugate base, as it is what is left. So we write down that formula. And there we go. We are done with 7.1. Now to move on to 7.2. 7.2 starts by reading that vinegar is a solution of ethanoic acid, CH3COOH. A certain manufacturer of vinegar claims that the vinegar she sells contains 5.8 grams of ethanoic acid per 100 milliliters of vinegar solution. A group of learners used the apparatus shown below to test the claim made by the manufacturer. They titrated a dilute sample of vinegar against a standard sodium hydroxide solution, NaOH, of concentration 0.1 mole per decimeter cubed, using the indicator as in the acid-base indicator, okay, which looks like HIN. Okay. The balanced equation for the reaction is given by the following: NaOH in aqueous plus ethanoic acid in aqueous gives us CH3COONA plus water. Write down the name of apparatus X. Right? It is called a burette. Right? This would have been done in practical. All right, and this would have apparatus X, which was this whole thing over here, is or this part here is called a burette. In 7.2.2, that was 7.2.1, using the equation in 7.1, determine the color change that will take place at the end point. Choose from pink to colorless, or from colorless to pink, and use Le Chatelier's principle to explain your answer. Well, if you look at 7.1, we definitely have to go from colorless to pink, and we need to use the equation in 7.1 to determine the color change that will take place at the end point, right? At the end point, okay? Here we're not having the, here we are using, over here we are titrating over here, so we need to have a look at the end point, okay? So usually this is what happens. This is usually, like they said, acid-base indicators, okay? The reaction of the indicator with water gives us from colorless to pink, okay? But now, okay, we have a different reaction. So this is definitely going from pink to colorless. Okay, this is the knowledge of what happens in titration. Okay, it's going from pink to colorless. Okay, and let's have a look at why. Well, when we add ethanoic acid, okay, by adding ethanoic acid, all right, we increase, all right, the hydronium ions. Okay, we increase H3O plus. All right, number one. All right, now the reaction that would consume hydronium. All right, the reaction that consumes H3O plus. Okay, is favored. All right, that would be favored. All right, and that reaction would definitely be the reverse reaction. All right, the reverse reaction in this case would be favored. All right, so let's say is favored. Another way we can say our final point there is to say that either the reverse reaction is favored, or we can say equilibrium position would shift to the left. It would also be a good considerable answer to put there instead of the reverse reaction is favored. This 7.2.3 is a nice question because that's calculations. 7.2.3, calculate the pH of sodium hydroxide solution before titration. All right, well, this is quite a basic question. We know that the concentration of the hydronium plus the concentration of hydroxide ions, right, must equal to the pH scale, which is 1 times 10 to the negative 14. They gave us the value of the concentration of the base, which was sodium hydroxide, which was 0.1 mole per decimeter cube. And we have hydroxide present here. So we substitute 0.1 in for OH minus, because it's the concentration of our base. Okay, acid would have gone in here. And we know that's equal to 1 times 10 to the negative 14, because the pH level goes up to 14. What do? We divide both sides by 0.1, and we get the value of H3O plus to equal 1 times 10 to the negative 13. Now we know that pH is going to equal negative log of whatever H3O plus value is equal to. And we know that we've just worked it out to be this value. So what we're going to do, we're going to say that equals negative log brackets 1 times 10 to the negative 13 on our calculator. And if we do that, we get pH is equal to 13. And that is the pH level of the, just scroll back down to the question, of sodium hydroxide before titration. And now 7.2.4, the bit of stoichiometry here. It says that the solution of vinegar used in the titration was obtained by adding 10 centimeters cube of vinegar to water and filling up with water to a volume of 100 cubic centimeters of dilute vinegar solution. During the titration, 18 centimeters cubed of sodium hydroxide solution of concentration 0.1 mole per decimeter cube neutralizes exactly 20 cubic centimeters of diluted vinegar. Determined by calculation whether the manufacturer's claim is true or not. Okay, well, let us have a look and see which one we get. Well, I think firstly, if we have the concentration of the sodium hydroxide, let's calculate how many moles we had of sodium hydroxide. So let's go perform this calculation over here. The number of moles of sodium hydroxide should be equal to the concentration times the volume. Now we were told the concentration was 0.1 right here, all right? And we said during titration 18 cubic centimeters of sodium hydroxide neutralizes 20 cubic centimeters of diluted vinegar. So 18 cubic centimeters divided by 1,000 would be 0.018 decimeters cubed, and we get a value of 1,8 times 10 to the power of -3 mole. Okay, and that would be the amount of moles of sodium hydroxide. Now, because they're all in the same ratio, okay, the number of moles of dilute ethanoic acid, which would be vinegar, is also equal to, so CH3COOH is also equal to 1,8 times 10 to the power of -3 mole. Okay, same mole ratio. Okay, now what we want to do is we want to find out, okay, what was the number or the concentration of dilute ethanoic acid. So the concentration of dilute ethanoic acid is definitely equal to the amount of moles, 1,8 times 10 to the power of -3, all divided by 0,02. And that should give us a value, I'll change the color here, that should give us a value of 0,09, pardon me, mole per decimeter cubed. Now, another thing to factor in the question, it says that the dilute solution of vinegar that was used in the titration was obtained by adding 10 cubic centimeters of vinegar to water. So we still need to calculate what is the number, or rather the concentration also of the undiluted vinegar. Excuse me. Okay. So what do we do with that? So we had 10 cubic centimeters there. So we take 0,09 and multiply that by 10. And the number of moles of the undilute is 0,9 mole per, or rather the concentration rather of the undiluted is definitely 0,9 mole per decimeter cubed, because we had 10 with the dilute acid we took 10 and then we filled up to 100, so we're just calculating the number of moles of the undiluted, or the concentration rather of the undiluted acid, which was 0,9. So what this means is 0,09 mole per decimeters cubed per 100 cubic centimeters, right, of the dilute. This is what that means. That's just the value of the undiluted acid. Now to come back, now we need to find out what is the mass. All right, just to go back to the question, they asked to determine whether the manufacturer's claim is true or not. Now, what is her original claim? All right, she claims that the vinegar she sells contains 5,8 grams of ethanoic acid per 100 milliliters. Okay, we need to prove if her claim is correct. So what do we do? There we go. What do? We first I need to get a new page. Here we go. So we take the formula, of course, N is equal to M over Bm. Okay, we know the number of moles was 0,09, which was the number of moles present in the 100 cubic centimeters. Okay, if we take the molar mass of vinegar there with CH3COOH, we'll get a molar mass of 60. Okay, multiply both sides by 60. Okay, and therefore the mass of ethanoic acid in 100 cubic centimeters is not 5,8 but 5,40 grams. all right, of ethanoic acid that's in 100 cubic centimeters. So is her claim true or is it false? It's definitely not true, or we can write just it is false. All right, it's not true. It is not 5.8 grams of ethanoic acid per 100 milliliters. It excuse me, is 5.4 grams per 100 cubic centimeters, in fact. And with that, wraps up 7.2.4, wraps up question 7. Please stay tuned for the next video. We will look at question 8.